Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 13th module, second lecture, that is 62nd lecture of this course, and this is mostly a recalling type as already we completed in the beginning. So these are all very important. Let us quickly recall floating point numbers. How floating point numbers would be used in the numerical computation, finite digit arithmetic, rounding, chopping. Then we go for the what we call errors and computation. How errors will be used in the numerical computation. The idea is the propagation of the error need to be controlled and the error should be minimized. Then we do have law of floating point arithmetic. Law of floating point arithmetic. Then addition of floating point numbers. How floating points would be added. How floating point would be subtracted. How floating points would be multiplied. How the floating points would be division can be taken. Then errors bounds. What is the least upper bound, greatest lower bound, and so on and so forth. Then round off errors due to cancellation. These are the things which we would like to learn in this particular lecture. Quickly, let us start with floating point number. So we define in the following way, that is a t digit floating point number. Floating point number in the base beta has the form x is equal to plus or minus m times of beta of e, where m is a t-digit fraction called the mantissa, and e is called the exponent. E is called the exponent. So as a matter of fact, if the mantissa is different to 0, if the mantissa is different from 0, if the mantissa is different from 0, then the floating point number is called, then the floating point number is called normalized. Then the floating point number is called normalized. For instance, if you have the numbers 0.3457 multiplied with 10 power 5. So this is 1, 2, 3, 4. So this is a 4-digit. Normalized decimal floating point. Normalized decimal floating point. Floating point number. Whereas 0.03457 into 10 power 6 is a 5 digit unnormalized. Is a 5 digit unnormalized. Look at this 3457 10 power 6. So if you multiply with 10 it is 0.3457. But this is a 4 digit normalized and this is a unnormalized number. So when you talk about this, this is a 5 digit unnormalized number. So if you want to have 4 digit, it is a normalized, but 5 digit is a unnormalized number. So same stuff can be written in both ways. One is the normalized, another is the unnormalized cases. Well, the number of digits in the mantissa is what we are calling as precision. So one can use single precision, one can use double precision, so in the single precision what we do is, in the single precision, so the maximum number allowed is, that is exponent is up to 8. Whereas in this case double precision, if you use it is exponent will be allowed up to 11. So that is the reason that the double precision will give you a better accuracy. So mantissa also in this case it turns out to be 23, whereas in this case the mantissa turns out to be 52. So what we can do is, we can do some simple example. Let us look at into the case where it is the underflow and overflow. Suppose let beta is equal, let's say it is 10 and t is equal to, let's say 3, and L is equal to, let's say minus 3, and U is equal to, let's say 3. So A is the number which is 0.111 into 10 power 3, and B is the number 0.120 multiplied with 10 power 3. So I wanted to compute a number called C is A multiplied with B. So that would be giving me 0.111 into 0.120 multiplied with 10 power 3 multiplied with 10 power 3. So I would be ending up 0.133 into 10 raised to the power 5. This is the number which I am getting it. This is what we call it as a overflow. This is what we call it as a overflow. Because the reason is the exponent 5 is too large. Because the exponent 5 is too large. The exponent 5 is too large, so therefore we call it as a overflow. Same thing can be interpreted, right? Got it? What I said? So if you take beta is equal to this number and I wanted to compute the numbers A and B in order to get the product. So I do end up with 0.133 times or 10 power 5 and 5 exponent is too large, which I call it as overflow. And for the case, let's say I will have, that is, let's say for the case of underflow. So let's say I will have beta is equal to 10 and t is equal to, say I have a 3 and L is equal to minus 2 and U is equal to, let's say it is 3. So A is equal to, I will have 0.1 times of 10 power minus 1 and B is nothing but 0.2 times of 10 power minus 1 and I wanted to compute C is equal to AB. So which is nothing but 2 into 10 power minus 4. So minus 4 is again a smaller number, so which we call it as underflow. So we wanted to have the system which should not be underflow, which should not be overflow. That is the basic idea of underflow and overflow. Now let us look at the rounding errors. What are the general ways in order to find out the error computation? So we will write this number. Let us consider the number plus or minus point d1, d2, dt, d of t plus 1 and so on and so forth like this. There are two ways as I spoke. One is what is called chopping, another is called rounding. Chopping and rounding. And we write it as FLX as the floating point representation. That is floating point representation. Representation of a number. Floating point representation of a number. Real number x. So we will have, let us first consider this what we call rounding. If you take rounding, let consider the base. Consider the base 10. Let's say base is 10 and x is equal to 3.141596 and for t is equal to 2, FL of x is equal to 3.1 and for t is equal to 3, FL of x is 3.14 and for t is equal to 4, FL of x is 3.142. So now let us see Error calculation. Now let's see error calculation. So what is the absolute error? Absolute error is, that is x cap minus x, and relative error is x cap minus x divided by norm of x, that is absolute value of x, provided x not equal to 0. Look at this, we consider this floating point number. When t is equal to, it is 3.1, 3.14, 3.142. Now absolute error is x cap minus x, and relative error is with respect to x, that is x cap minus x upon mod of x for x not equal to 0. So what we can do is, in many of the applications as we see these days, the relative error makes more sense. Relative error makes more sense. The relative error makes more sense. So for example, x1 is equal to, let's say, 1.31 and x1 cap is 1.30 and x2 is equal to 0.12 and x2 cap is equal to 0.11. So now I wanted to find out x1 cap minus x1, that is x2 cap minus x2, 0.01. So relative error is x cap minus x1 upon x1. So that would be equivalent to 0.0076335. Point 0.76335. This is what is the 0.7365 in the first case, right? This is for the case of these values, and for the second case, if you do it, that is x cap minus x1 upon x cap minus x2, that is x2 upon mod of x2. For this case, it turns out to be 0.083333. This is the error which you get it. So when you make this in both cases, the conclusion is the following: relative error is close to the approximation. Whereas absolute error nowhere close. Close to the approximation. Nowhere close to the approximation. Okay. So when you have this round of errors, so there is a theorem, that is how the floating point number should be constructed, that is absolute value of floating point of x minus x divided by x. This is less than or equal to mu. Mu is some number. So this is what we call it as 1/2 times of beta raised to the power 1 minus t for rounding. and this is beta raised to the power 1 minus t for chopping. So therefore, when you write this x is equal to, it is point d1, d2, d3 like this, dt, dt plus 1 and so on and so forth, multiplied with beta power e. Beta is the base, e is the exponent, and these are the mantissa. You can see some examples. So for example, decimal number, let's say I have x is equal to 0.2346. Let's say beta is equal to 10, t is equal to 3. So floating point of x turns out to be 0.235 and the relative error is 0.001705. So which will be less than or equal to 1 by 2 times of 10 power minus 2. Suppose if same chopping is used, let's say that. So then in this case it becomes floating point of x turns out to be 0.234 and this turns out to be, that is 0.0025575 into 10 raised to the power minus 2. Okay, so there are many more examples in a similar fashion how we can able to find out the floating point representation. This is very, very important in the numerical competition, how you would be computing 2 point, 3 point, 4 point, using chopping, rounding, and this law of there is a law of floating point arithmetic in general, that is called floating point arithmetic. The formula which we can write as, that is floating point of x minus x upon mod x. Floating point of x minus x upon mod of x. This will be less than or equal to mu, which will be equivalent to, that is beta raised to the power 1 minus t for chopping, and this is 1 by 2 times of beta raised to the power 1 minus t for rounding. So that can be written as, that is floating point of x, that will be equivalent to x times of 1 plus delta, and where this delta is less than or equal to mu. Delta is less than or equal to mu. So we can see some examples over here. How this floating point numbers can be done using the For example, if you look at this, let's say x is equal to 0.9999 times of 10 power 2. Let's say y is equal to 0.111 times of 10 power 0. So I want to find out x plus y, which will be equivalent to 100 point, that is 0.110, which is equal to 0.1000011 times of 10 power 3. So when you have this equations, x is equal to 0.9999 times of 10 power 2 and y is equal to 0.111 times of 10 power 0. So I can have a division x upon y, that will be equivalent to 900. That is floating point of x upon y. So which will be equivalent to 0.900 multiplied with 10 power 3. So delta is equal to 0. So this will give you a better approximation, as we could see from this concept. Well, there are many more examples like this. Let us now look into the addition of floating point numbers. How actually you could able to add these floating points, and what is the law behind it. See that the addition of two floating point numbers is same way, the way which we did it, that is floating point of x1 plus x2, two floating point numbers. So the addition of the floating point numbers using rounding, floating point numbers using the rounding. Let us start with n floating point numbers. N floating point numbers, let's say x1, x2, xn. Let's say n floating point numbers. Then let me define s of 2 is a new number which would be floating point of s1 plus floating point of x1 plus x of 2. Two numbers, floating point numbers. So which would give you s2 is equal to, I can write it as floating point of x1 plus x2, which I can write it as x1 plus x2 times of, that is 1 plus delta 2. So that means floating point of the numbers is approximated to 1 plus delta 2. Well, there are many more concepts like this. So there is a rounding error in floating points. So I write it as floating point of x1 plus x2 plus etc. xn, which is nothing but x1 plus x2. Like this you will have xn, and this is approximately equivalent to, so you can write x1 times of delta 1, s2, s3, like that you will have, and you will have a s of delta n, and ultimately you will get x1 times of delta 1, delta 2, etc. delta n. So similarly you can define the number ni, right? So similarly one can do the multiplication also. There is a theorem for multiplication. Floating point of x1, x2, xn is approximately equivalent to 1 plus epsilon times of the product pi I is equal to 1 to n xi. So which can be written as, where epsilon is nothing but 1 plus delta 2 times of 1 plus delta 3 times of, like that you will have, so that is 1 plus delta n minus 1. So suppose assuming that n minus 1 is multiplied with mu less than or equal to 0.1, then you will have, so epsilon is less than 1.06 times of n minus 1 into mu. So knowing the epsilon well in hand would help us. How we could able to control. Similarly, you can have the what you call different multiplication of the numbers. So that is the relative error in computing the product of n floating point numbers. numbers. That is the relative error in computing the product of n floating point numbers is at most 1.69 n minus 1 mu times of n minus 1. So you can have the multiplication of two numbers as defined in this case. We also do have what we call the inner product multiplications, the way which we did it in the round of errors. So we can write it as floating point of x transpose y is nothing but floating point x transpose x multiplied with y minus x transpose y. So this is less than or equal to pi times of n mu times of mod of x transpose x y, where mod of x is vector with components mod of xi and that is phi of n is a small function of n. Is a small function of n. And when it comes to the that is, look at into this theorem. Mij, two floating point numbers and C is mu times of C of A. Second one is floating point of A plus B is equal to A plus B plus E, that is mod of E is less than or equal to mu times of A plus B. If A and B are two matrices, compatible for matrix multiplication, then floating point of AB is equal to AB plus E that is E is equal to less than or equal to n into mu of A and B plus big O of mu square. So then what is the meaning of this mu square? So which is bounded by the expressions. Complicated expression bounded by mu square. So that means whenever you do floating point of AB, it does mean that AB plus some error. AB plus some error. So that is the reason that we write it as norm of E P is less than or equal to n times of mu norm of AP norm of BP plus big O of mu square. P is equal to 1, infinity or F. That is one norm, infinity norm or Frobenius norm as we did in the previous case. That's how we compute the norms for a particular problem. So, well, in continuation to that, round of errors due to cancellation. How round of errors would be cancelled, get together. For example, if I have a number x is equal, let's say 0.54617 and y is equal, let's say 0.54601. Let's say d is equal to x minus y, that is 0.00016, and x cap is 0.5462 and y cap is 0.5460. So that is d cap is x cap minus y cap, that is 0.002. How good the approximation is? So we wanted to have d minus d cap upon d, that would be equivalent to 0.25. So which is a bigger number. So this phenomena, that is the number, let's say 0.5462, it's the 4 digits, and 0.5460, they are almost same. So when the first one was subtracted from the second one, most significant digits got cancelled. Right? When you subtract, find 4562 from 4560, most of the digits they gets cancelled, and very least significant digit was left in the answer, that is 0.0002. This phenomena is what is called catastrophic cancellation. Catastrophic cancellation. Catastrophic cancellation. So many times what happens is we need to avoiding cancellation. Avoiding the cancellation. So you will have ax square bx plus c, right, for a not equal to 0. So you will have x1 is equal to minus b plus b square minus 4ac divided by 2a under square root, and x2 is equal to minus b minus b square minus 4ac divided by 2a. So the catastrophic cancellation, when you do it, very small value is being left out. Very small value being left out. So therefore, one would see that, in fact, let's solving this equation, ax square bx plus c is equal to 0. Ax square bx plus c is equal to 0. Let's say a not equal to 0. And put a is equal to 1, b is equal to minus 10 power 5 and c is equal to 1. So if the beta is equal to, let's say, 10, t is equal to 8, L is equal to minus u is equal to, let's say, minus 50, and your x1 will be equivalent to 10 power 5 plus 10 power 10 minus 4 divided by 2. Similarly, x2 will be equivalent to 10 power 5 minus 10 power 5 divided by 2, which is equal to 0. So completely wrong, and this is true. Right? This is completely wrong, and that is true. Well, we'll see some more examples in the next lecture, and especially some examples I wanted to do it. I'll stop over here for today's lecture. Thank you very much for being with me. Thank you once again.